try this one more time. Thank you, everyone, for coming to this talk. I'm very excited to be here and to be talking about this stuff. I'm also very excited to make this terrible joke that has been on my mind for like 3 years. So thank you very much to the organizers for letting me use this as my talk title. My name is Ramsey Nasser. I'm a game designer, a computer scientist, and an educator, and very recently the CTO of a company called Arcadia Technologies Incorporated. Arcadia Technologies is a company that develops and maintains the Arcadia open source project. And Arcadia is the integration of Clojure, which is the language that we're all here to talk about, into the Unity game engine. Has anyone here used Unity, played with Unity? A couple of people? So Unity is one of the leading game engines in the video game development industry. Something like 50 to 60% of all titles on mobile devices are actually written in Unity, depending on who you ask. And Arcadia is the project that brings Clojure programming into that game engine. So it's a 5-year-old open source project. We actually celebrated the anniversary of our first commit 2 days ago. April 17 is commit day, so it's exactly 5 years old this week. Arcadia is a Clojure framework built on top of Clojure CLR, which is an implementation of Clojure in C# that targets the C# runtime. CLR stands for the Common Language Runtime, which is broadly equivalent to the JVM. It's an acronym that I'll be using a lot in this talk. And Unity itself is scripted in C#. So its user interface and all of your game logic, you write that in C#. It's built on top of the Mono virtual machine. And that's how we're able to bring Clojure into Unity, because they have a common runtime, basically. So there's a community of people that has sort of blossomed around Arcadia. Like nothing fills me with more joy than that. Dozens of games have been made for game jams. A couple of Lisp game jams, actually, have been made in Arcadia. So it was like nice to get a Lisp game jam shout out. It's also nice to be not the only game talk at a Lisp conference, which we tend to be. It's like now there's 2. That's double. It's trending up. So we've been working on it just as a sort of side project for many, many years. And as of last year, we managed to secure some funding to start this company to work on it full time. So this is a very exciting moment of transition for us. This is a screenshot of a game called Swapland that a bunch of people from the community came together to make for a game jam. And this is a live stream of Joseph Parker working on Swapland. This is also the very typical, this is the workflow that you'll see in like Arcadia a lot. You'll have your Clojure editor and REPL open in one window, and your the Unity IDE open sort of in another window, often side by side. I'm 50% of Arcadia. The other 50% is my collaborator, Tim Gardner, who couldn't be here. But we've been working on this together since day one. Tim's actually taught me Clojure. Arcadia is my first Clojure project, so 5 years later, here I am, I guess. And none of this would have been possible without our collaboration, which is one of the best parts of it. So the goal of this talk is to answer these questions. These are questions that we get asked a lot as the Arcadia maintainers. We brought Clojure into Unity, but what does Clojure video game development really mean, right? Like, what does it actually look like tangibly? And there are different answers to this, right? There are different interpretations of what functional programming is. There are different interpretations of what video game development is. But my hope is to give you all some concrete examples of some stuff we've worked on in the last year, and start talking about some of the challenges and trade-offs that we find that we have to make, or that we get to make as Clojure game developers. Our caveat is that I'm going to be showing you some game prototypes that Tim's and I have worked on. We spend most of our time making Arcadia and not actually designing games. So we tend to make the least interesting stuff in Arcadia. The community has actually made much nicer, much more interesting games that we're not gonna be looking at. But we're gonna be looking at some simple prototypes instead that more directly speak to this question. They'll be a little bit easier to pick apart. So just keep that in mind. The other very important caveat is my favorite quotes from weird Twitter. There are no sweeping truths here. There's no single answer to any question. Everything is going to depend on what you're doing, what your context is, who your users are, and what kind of game you're trying to make in our case. So keep this in mind for everything that I talk about. Also, if you can hear my fan spinning up, that's the sound of an entire GPU capturing like slides. This is kind of hilarious. I hope the mic isn't picking it up. So with that in mind, a place to start this conversation might be to talk about why not Clojure? Why not functional programming? Clojure in particular and functional programming in general have seen pretty sizable uptake in a variety of software engineering industries. ML and Haskell get used at places like Facebook and the Target, I think, for like managing their warehouses. Clojure, of course, gets used in the front end, the back end, and a lot of companies. But the games industry has been very hesitant to adopt functional programming as an idea, and certainly any new programming languages that aren't C++. So it makes sense, I think, to start this conversation by asking why that is. Another way of thinking about this is what is different about game development compared to other kinds of software engineering? So I actually had a bunch of slides here that was like trying to communicate my experiences as a game developer and going to the Game Developers Conference and like what the feeling in the room is in like game developers when you're talking about functional programming. But I actually found a quote by John Carmack that sums it all up. So I deleted all my slides and we're just going to look at that quote. Who here knows who John Carmack is? Actually don't. Oh, okay. So I'll cut my intro in half. So John Carmack is famous in the games industry for having worked on Doom, Wolfenstein 3D, Commander Keen, really genre-defining games. And he's this celebrated architect and industry veteran. So the quote we're going to look at is valuable because this is the voice of someone who's like very, very elevated in the industry. He's also interesting too because he has actually dabbled in functional programming and Lisp in particular. Around the time this quote was written, he was getting into Haskell, getting into Lisp, and he famously ported a big chunk of Wolfenstein into Haskell into a functional style. So he's someone who's like sort of had a foot in both worlds, much more in one than the other. But he's not talking about functional programming from a place of ignorance. That said, let's look at his quote. So it's short, so I'm going to read it in its entirety, if that's okay. The emphasis is mine. I do believe that there is real value in pursuing functional programming, but it would be irresponsible to exhort everyone to abandon their C++ compilers and start coding in Lisp, Haskell, or to be blunt, any other fringe language. To the eternal chagrin of language designers, there are plenty of externalities that can overwhelm the benefits of a language, and game development has more than most fields. We have cross-platform issues, proprietary tool chains, certification gates, licensed technologies, and stringent performance requirements on top of the issues with legacy code bases and workforce availability that everyone faces. If you are in circumstances where you can undertake significant development work in a non-mainstream language, I'll cheer you on, but be prepared to take some hits in the name of progress. This is an article called In-Depth Functional Programming in C++ that he wrote in 2012. So there's a lot to unpack there, right? First of all, fringe languages. Ouch. It's not very nice. But he specifically calls out game development as somehow categorically different from other kinds of software engineering. And he's not totally wrong. When he's talking about proprietary tool chains and certification gates, he's talking about getting code to run on a PlayStation, trying to get code to run on an Xbox or a Nintendo DS. These are, the only console work I've ever done is on the PlayStation, and from that experience, I can say that that platform is extremely locked down. And in order to even get access to development hardware, which is physically different from the PlayStation that you buy in a store, you need to enter into basically a business relationship with Sony and go through all kinds of jump through all kinds of hoops just to even get your hands on hardware to then even begin testing your new programming language against. So in many cases, this is just a non-starter, right? So the games are unique in that they, in many cases, will be targeting very exotic and very strange platforms beyond just the desktop and the server and the browser. And he also calls out stringent performance requirements, which we're going to look at in depth next. So the bulk of this talk is going to be talking about functional language performance in games. But I also want to call out that this is just the perspective of one person, sort of an elevated person, an important person, but he is just one person. Historically in games, many languages have been used. Lisp has been used in many, many games. Has anyone played Jak and Daxter, Crash Bandicoot? Yeah. So my understanding is that most of the Jak and Daxter games were like written in Lisp. There's a language called game-oriented assembly Lisp that was developed by the company Naughty Dog that a lot of their games in the 90s were built in. My understanding is that it's still around in some diminished form, but there have been games written in Forth. So people do other things, and certainly if you're targeting the browser, right, you'll be writing stuff in JavaScript. And so this is a perspective of someone in the AAA, high-fidelity, high-budget games world, right? It doesn't speak for the whole industry, but it's a good sort of place to begin our conversation. So stringent performance requirements is something to really look at, because this is where functional programming gets tricky in games. And to talk about performance in games, we need to get a sense of like how a game works and what performance means in a video game. So who here has ever like tried to make a game or made a game or played around with game stuff? Oh, okay, a bunch of people. That's great. So if you've done that, you've very likely been exposed to some version of this. This is a very simplified, pared down main loop of a game. What a video game is a system where you gather inputs from the outside world, keyboard inputs, mouse inputs, joypad inputs. You use those inputs and the current state of the game to mutate the state of the game into a new state. You use that new state to mutate the render state, which is where everything is and how they look. You hand that render state off to OpenGL or DirectX or Vulkan or whatever, and the user gets pixels on the screen. And then you come back and you do that again. So the performance of a game is how many times can you do this in 1 second, right? So as fast as possible is the way it sometimes gets talked about, but that's not terribly helpful because this will never be 0. And it turns out that there is actually a cap or a couple of caps. There is such a thing as fast enough. And games tend to have what's called a target frame rate. So this is the goal where if we can produce this many frames a second, we're going to call this game smooth enough, right? And any extra effort is actually not worth it. That number tends to be 60 in a lot of places, 60 frames per second. That tends to link up with the refresh rates of monitors. So in many cases, even if you're producing more than 60 frames in a second, your monitor isn't really going to be able to show you more than 60 frames in a second. So it doesn't actually make sense to continue optimizing anymore. In some cases, it'll be 30. In old Flash games, it was actually as low as 12. Like some of the older Flash games had like really low target frame rates. But we're going to use 60 for the bulk of this talk, because that's the high watermark of video game performance. It's a little different in VR. Strictly speaking, in VR, because you're rendering 2 frames at a time, you kind of need to hit 120 frames per second. But that's a whole other conversation. So 60 frames per second means you have 16.6 milliseconds repeating to go around this loop. If you can gather inputs, update state, update render state, and render to the screen in 16.6 milliseconds consistently, you have a fast game. That's it, right? So the goal is not 0, right? There is some kind of concrete goal. Also something to keep in mind, all the conversation today is going to be single-threaded. So multi-threaded programming is beginning to make its ways into game development, but for the most part, game engines are single-threaded systems where your game logic and your render logic runs synchronously on a single thread. So we're going to be talking about Unity specifically, and we're going to be using, I have a bunch of screenshots of Unity's performance tools that we're going to use for our analysis. This is a screenshot from their CPU profiler. And the way to read this is a graph of the performance of a game written in Arcadia over time. Both the x and y axes are time. The x-axis is time in frames. So every column of pixels is a different frame of the game as it was playing forward in time. The y-axis is how long that frame took. And you can see that it's color-coded, so you can see what portion of each frame went to different subsystems within Unity. So in this game, we only have 3 subsystems that are running. So the rendering is the green band at the top. The bulk of it in the blue is the scripts. That's the actual game logic that's running. And the little burble at the bottom is the physics. There's a little bit of a physics simulation, probably for collision detection, that took a little bit of the frame as well. You also see cutting across horizontally a couple of guidelines. So we have our guideline for 60 frames per second, rounded down to 16 milliseconds. We have a guideline for 100 frames per second and 200 frames per second, which are not terribly useful, but they're there just so you know like how fast or really how much space you have to expand to get to your like 16 millisecond frame budget. Does this visualization kind of make sense? The track? Cool. So this is similar if you've ever done, has anyone ever used the performance tools in Chrome to like monitor JavaScript performance? Yeah. So this is a similar idea. It's visualized a little bit differently, but this is the same basic idea. You have frames and you want to know how long each one takes. So what are the performance challenges for Clojure, given that we have a better sense now of what the stringent performance requirements are for a video game, right? What is it that is hard for Clojure or to meet those, or what are the challenges that come up when we try to meet those requirements using Clojure? So Clojure is not a slow language. It's like important to like call out. It's a dynamic language, but it's not a dynamic language in the way that Ruby or Python are. Clojure is compiled. It compiles into the bytecode of its host. And the compiler makes actually quite a few clever optimizations. So the performance problems that you'd have in Ruby, for example, are very different from the performance problems you'd have in Clojure. But what we run up against in Arcadia all the time is allocations. So an allocation is code that stores data in the heap area of memory as opposed to the stack. And in a garbage collected runtime, storing data to the heap means that that data will have to participate in garbage collection over the lifetime of that data. So if that data is no longer used, it'll have to be collected at some point by the garbage collector. If it continues to be used, it'll have to be scanned for pointers. It introduces what some people call garbage collection pressure. There's an increased pressure on the system the more stuff you're putting into memory. Unity is unique and somewhat controversial for having a runtime garbage collector among game engines. There are a lot of like old school game developers who are friends of mine that avoid Unity because of that, because they feel that the cost and the burden of having a garbage collector is not actually worth the performance trade-off. I make games in Clojure, so I obviously don't agree. But it's made a little worse by the fact that Unity's garbage collector happens to be quite terrible. For a variety of implementation reasons, they're sort of stuck with a 2008 era Boehm garbage collector, which is a conservative garbage collector that can't do all kinds of interesting optimizations. And they're making improvements to it, but I don't really expect that to change in a categorical sense anytime soon. So Clojure is designed for a multi-threaded applications with a good garbage collector on the JVM, and we're trying to make it work in a single-threaded context with kind of a crappy garbage collector. So we have our work cut out for us. And the way garbage collection manifests to the user is when the garbage collector steps in to collect your memory, it stops the world. So your game freezes for a certain number of milliseconds while your memory gets cleaned up and then resumes. So the user will see a stutter. That's kind of how it manifests. It's also important to separate out, it's not that all allocations are bad or a problem, right? You couldn't write most useful programs without some kind of allocation. So I separate them out into what I call essential and incidental allocations. These are not formal terms. These are just words that I made up to like make the next few slides a little more concrete. So if you Google them, I don't know that anything will come up. So there's two kinds of allocations that I want to look at, which is important because we kind of have a plan for dealing with one of them, and we don't really have a plan for dealing with the other. So here's a snippet of the kind of code you might write in Clojure on a daily basis, right? Can everyone read that okay? Does that look okay in the back? Cool. So you got some data, you throw in a threading macro, you associate some stuff onto it, you sort of selectively merge the results of a function call, depending on a predicate, and then you dissociate a key from it, right? No problem. Every one of these steps involves multiple allocations, right? Functional programming is predicated on the idea of not changing things. And not changing things means constantly making new things. And the way you make a new thing is by allocating space in the heap for it, generally speaking, right? So these allocations strike me as a kind of essential allocation. They capture my intent as a programmer. Like I intend there to be, a couple of new hash maps generated in the run of this code, right? That is my intention. It's almost the cost of doing business in functional programming, right? It comes with the territory, right? You're going to be doing a lot of allocations. In theory, I guess a very clever compiler could look at this and do some escape analysis and figure out that actually we can turn your hash map into a transient for you and do some clever stuff here and there. Maybe, I don't know. But there isn't an easy answer to, in the general case, eliding the allocations that arise from just normal functional programming semantics. So that's the first category. The second category is what I call incidental allocations. So here's a function that takes two three-dimensional vectors, computes the midpoint, and returns them. If we were to have written this in C#, it would not allocate any memory. Indeed, there's nothing in here that really is very deeply functional, right? It's just linear algebra. So it's almost surprising to some people that this does actually incur garbage collection pressure. But because of the way Clojure was architected, functions all take a reference type, an object, as their arguments. So every argument to a Clojure function needs to be coerced into a reference type. And in Unity, three-dimensional vectors are structures. They can be stack allocated. In fact, they're designed to be stack allocated explicitly to avoid garbage collection pressure. But because of the way hyphen works in Clojure, by default, the vectors that we construct will actually be moved to the heap before they're passed into the function. And they will have to be collected. They will incur garbage collection pressure. So this is the kind of allocation that does not capture my intent as a programmer. I didn't intend there to be allocation. I'm not doing heterogeneous dynamic data structures, I'm not processing them in a functional way. This is an implementation detail of the compiler that has a cost, a performance cost. So I term these incidental allocations. The good news about these is we do actually have a solution to them. So Magic is a compiler that I've been working on and off for the past 2 or 3 years. It is a Clojure compiler written in Clojure that targets the common language runtime. And its explicit goal is to eliminate incidental allocations. Magic can compile about 40% of Clojure right now. It can't compile the standard library, but it's a very large subset of the language. And we have seen it take allocations down to exactly 0 in many cases where we've used it in mostly sort of linear algebra style code like this, which is very prevalent in games. So this is a topic that I've talked about in other conferences and other contexts. There's hours of me talking about this stuff online. It's out of scope for this talk, but if you want to grab me afterwards, talking about bytecode is my favorite thing. So please don't hesitate. So that's performance in video games and the challenges that Clojure presents. And with that, we can start looking at case studies. But how's everyone feeling? Does that sort of make sense of things? Great. So the first prototype I want to look at is what I think people tend to think of when they come to Arcadia, when they think about Clojure in video games, which is just fully functional game development. So the prototype, is the video playing? Yes. Nice. The prototype that we made is a very pared down, very basic implementation of Texas Hold'em poker. Here I'm playing as all the players, and the game is advancing by my clicking on buttons at the bottom of the screen, if that's not totally clear. So this is a game that I made with Tim's last year in collaboration with a Singaporean game development company called Flybot. And I want to give a shout out to Isaac Johnston, who did a lot of the work on this. And working with them was an absolute dream. But this was kind of an experiment in how functional can we get? So what we did was Isaac ported Reframe to Arcadia. Has anyone used Reframe? A couple of people? Oh, great, awesome. So Reframe, if you haven't used it, is a functional declarative framework to build single-page applications in the browser. Porting it to Arcadia, sticking with the Arcadia theme, we named it Pastoral. So Pastoral is the Reframe port that integrates into Unity and Arcadia. And the whole game was built in Pastoral. So let's look at some snippets. So reframe and pastoral are all based on there being a single application database that is a single source of truth for all data in your application. Pastoral is the same. And you update that database by dispatching events. So this is the code that's hooked onto the buttons in the poker game. When you click on a simple button, you just dispatch an action event with some associated key. So the all-in button, the key would be all-in. The fold button, the key would be fold. So here you're dispatching poker actions in the vocabulary of poker itself. An input button is similar, but it takes data from a text box, and it includes that in the event. So this is what the raise button uses. You enter in like how much you want to raise by, and you click raise, and that dispatches off into the database. This is the handler for the action event. It extracts some, it extracts the values from the action, as you'd expect, and it passes the event off into game step, passing in game, which comes out of the application database, if you could see that on the third line. So what this is doing is getting some event from the outside world. It's getting an immutable representation of the game state out of the application database, passing it to game step, which is a purely functional implementation of poker, and we're getting a new game out of it. From that new game, we derive the scene. So we figure out where all the cards should be. We figure out how all the chips should stack. And then we update the database with that information. So nothing is mutating anywhere, right? It's completely functional. Even our animations are sort of tend functional. So all the animation code was written in Clojure as well. They maintain local state, but you're able to compose them in a way that's really nice because of Clojure semantics. So when you move things in space in a game, generally what you want to do is you want to, every frame, move them a little bit closer to their target. And then when they're close enough to their target, you actually want to snap them to the final spot. If you don't do that, then inaccuracies could accumulate, and your objects may not actually be where you think that they are. So we have a move to function that takes an object, where you want it to go to, and how fast you want it to get there, sets up some volatiles, and then gives you a function that will mutate. Get my cursor here. I actually can't see my cursor. But if you see you'll see some mutation to things called transforms. Does everyone see those? The set bang, dot dot transform local position. We're also accessing dot dot object transform local position. So these are elements of the Unity scene graph. So we're actually reaching in and using interop to move things around visually in front of the user. But it's all wrapped in a Clojure function that's going to be evaluated over multiple frames. And because it's all built on these little functions, at the very bottom where I've highlighted in green, we can just stitch together these animations. So even our animation system, which bottoms out and just mutating the scene graph, because it's built in Clojure, we get this really nice composability. We can just mix and match animations as need be, and the thing that runs is actually quite fast, because it's just doing interop. So all the details of this code might be a little obscured, right? Because it's sort of extracted from a much larger framework. But I just wanted to hit on a couple of touch points just to give you all a sense of what this development looks like. So now the question is, what does the performance look like? This is a screenshot from the profiler as I was playing the poker game. Any guesses what the spikes correspond to? So they're actually not, it's actually not GC in this case. They're blue, just like in the first example. This is code running. So the spikes correspond exactly with me clicking on a button. And that low burble is the rest of the game. So the game is actually comfortably under 60 frames per second for most of its existence. But when you do an action, functionally computing a new poker state, functionally computing a new layout, functionally setting up all the animations, getting all your ducks in a row there, that drops us to almost 15 frames a second. But then we're back, because everything that you set up just runs like a wind-up toy. So this is the profile of the poker game, right? So because something we didn't do, just because we ran out of time more than anything else, is because the updates, so many of the updates are functional, we could have moved a lot of the stuff probably to another thread. Now, Unity runs on, Unity scene graph and renderer all run on a single thread. But you're free to use other threads if you want, right? You just have to get the synchronization right. And Clojure makes that very easy. So in theory, this is like these spikes that we're seeing, which is just the cost of just doing functional programming. We could, in theory, move them to another thread. And this is stuff that we're experimenting with this year. So what are the trade-offs? All the development is driven in, is done in a REPL, which that alone to me is like a categorical improvement over traditional game development, which is, hit play and then exit, edit code, hit play, exit, edit code. Because it really is just no-holds-barred functional programming, we are leveraging all the expressive power of Clojure. So everything that you know and love about Clojure is coming to full force in this game. And we're even reusing a popular Clojure framework. Part of why Arcadia is based on Clojure and not some programming language that we made up is to take advantage of the ecosystem and all the stuff that people did. And this is an example of us being able to do that. What we sort of lose in exchange for that is our performance is going to degrade as the frequency of our events increases. And I'd even go so far to say that our performance would probably degrade as the size of our game increases. So here we have these nice single frame spikes. I mean, they're not nice. I feel like I'd get fired by like some clients if I was like talking about this as if it was okay. But you get this like single frame spikes, which are manageable, right? You'll often not see them or like notice them. But I would imagine that as the game got bigger, they would start to widen out. And we'd get like longer sort of like multiple frame gaps. But it works in this poker game because it's kind of a small game. So this is an approach that I think in general could work for small event-driven games. And just to make sure that you understand, I'm not deriding small games. Does anyone recognize this? Has anyone played this? So this is Candy Crush Saga. This is one of the best-selling games on mobile. Does anyone have a sense of how much revenue it's pulled in its lifetime? So the last I checked, it was pushing 4 billion. So small games are not toys. They're arguably some of the most lucrative games you can make. This is the kind of game that I think the amount of stuff you're dealing with, the frequency of events are low enough that I think they could fit within the performance profile of something as purely functional as what we did for the poker game. So really, if your game is small enough, you could just do it. Fully functional game development is not off the table in the way that I sometimes feel like it's talked about. But that's not actually what Arcadia does out of the box. Pastoral is its own framework, and Arcadia's goal is to integrate with Unity. And by design, Arcadia is fairly low level. And we try and walk this tightrope between tracking Unity's semantics while remaining true to Clojure. And in many cases, those things are in opposition to each other, and we need to make a kind of a judgment call. But the result is that Arcadia out of the box is more of a hybrid system. So this is another game that we put together a couple of weeks ago in Arcadia, which is much more sort of fast-paced. It's a standard tube shooter where you sort of like swing around a tube, and enemies come at you, and they shoot zaps at you, and you shoot zaps back, and you try and not get blown up. This is, so the examples we're going to look at are Arcadia's native handling of behavior and state. And the basic philosophy in Arcadia is to use Clojure for interesting game logic, and then let Unity do what it's good at. So in this game, the particle systems and the particle effects, that's all Unity. Arcadia has nothing to say about that, because Unity's good at rendering and managing particle systems, and it's not particularly interesting for us to have a functional representation of every particle in our space. It'd be nice, but we could live without it. The logic of how the enemies work and how the bullets work, all of that is written in Clojure. So the mindset that Arcadia tries to give you, really the abstraction that we try and offer on top of Unity, is you could think about all the objects in your game as data. Really as kind of like these associated data structures that are more or less hash maps. And an object in your game can have a number of what we call roles. So here's a sketch of a hash map. This isn't from the game itself. This is just an illustrative sketch that has two roles. It has a runs role and a fades out role. So runs has a thing called state and a couple of other keys. And a role in Arcadia decomposes into state and what we call hooks. So state is a value that may be pure or mutable, it's up to you, that is associated with each role that maintains its own local state. And then hooks are functions that you attach to Unity events to run whenever the engine decides that an event has occurred. So what the runs role is saying is that my speed or my state is a hash map where the speed key is 20. When on every Unity update, call this movement runs var. And on every on collision enter event, run this movement bump var. So update and on collision enter these are Unity events, right? Unity will decide when two objects have touched and run that function for you. The fades out role similarly has an on destroy hook, where when this object is destroyed, run this fade out function, but it has no state. So this is the sort of mental model that Arcadia tries to present to you on top of just raw Unity interop. So this is how it manifests in code. So this is the logic that removes bullets after a certain amount of time. So Arcadia provides a thing called def mutable, which is like def record, but it's mutable. And it integrates nicely into our APIs and can be snapshotted. And we have a def role macro, which I'll expand in the next slide, that is just basically some syntax sugar. GO in these slides stands for game object. So this is a function that's acting on whatever game object you've associated this role with. And game objects are just all the things in the scene. So we look up the state, and K is the key that role is associated with, because everything the whole thing is an associative data structure. So every frame, we're going to look up our local state. So we're going to grab whatever bullet age def mutable is associated with this role. I'm going to decrement it by delta time, which is the amount of time that has passed between this frame and the previous frame. It's usually a very small number. And when the age is less than 0, I'm going to destroy this game object by calling retire on it. So def role just expands into this. So we generate named vars for you, and we generate that hash map that is effectively the role. And then in true Clojure fashion, you build bigger abstractions on top of that abstraction. So the whole bullet, the age and remove, is just one aspect of its logic. It also has a tube position, which is the logic that places the object along the tube. So there's something that maps between the two-dimensional position on a tube and the three-dimensional positions in space. It has a world position that also participates in that. Bullets have health, and they can damage things, right? So these are the sort of separate roles that make up a single bullet. And when we spawn them, what we do is we ask Unity to instantiate what they call a prefab, which is basically a collection of assets and game objects. And then we just assign new roles to it on its way out. So it's almost like a step in a pipeline, where we ask for a new bullet, we get a thing with all the particle systems, all the colliders, all the Unity-specific stuff. We give it all the Clojure magic, and we send it on its way. Now, this is very powerful, because what we're doing here is we're merging this bullet hash map, which we define statically, with new information. In the top sort of green highlight, you can see that we're actually changing the states of the to position and the age and remove using this merged states helper function that we have. You can get much more advanced with that, beyond just updating values, which you could do in if you're just creating components as instances in an object-oriented programming. You could say, so this is not in the game, but you could say that while you're spawning the bullets, selectively merge into the roles of that bullet different movement logic, if you want, depending on how much time has passed. So medium bullet, hard bullet, and impossible bullet here might have their own update hooks. They might have their own on-collision hooks. They might do something wildly different. But you have this, you could think of your objects as data at development time and even at runtime. And this is something that becomes very difficult to do with just traditional object-oriented C# component-style programming. So Tim's put together this really great graphic that sort of illustrates what we're trying to get at. And it contrasts these three different ideas of state and time. The classical game development and Unity-style approach is you just have mutable state, and that just updates in place, and that's the whole story, right? You're just sort of marching forward in time, mutating yourself, and I hope you don't mess it up. The reactive model, which is what React does and what Pastoral does, is you have an immutable representation of the data that makes up your entire application, and you can derive a presentation from that using a pure function. And then given some inputs, you compute a new data for the entire application. Arcadia is different from that. Arcadia is sort of bottoms out in the Unity thing, where we are this mutable machine that's marching forward through time. But you can selectively turn data into these mutable little machines, and you can turn these little mutable machines back into data by snapshotting them. So you can round trip the Clojure immutable view and the Unity mutable view. And this is the compromise that we've struck in Arcadia. This is how we're trying to have our cake and eat it too. So, part of the intellectual trade-off that we'll see in a second is that you need to be more explicit about this. We can't have functional programming everywhere for performance reasons, for the kinds of games we're trying to make with this, but you can have a lot of functional programming. You just need to be selective about where you do it, where you don't do it. So how does it hold up? So we're seeing spikes again, but now the spikes are brown, which is a color that we have not seen yet. So these are garbage collection spikes. And these don't correspond to any action that I took in the game. They just happen whenever the garbage collector decides that they happen. Most of the game is under 16 milliseconds, though. Most of it comfortably under 16 milliseconds. But we do have these spikes. The good news is we believe that a lot of this is incidental allocations. And we believe that magic could actually iron a lot of this out. Maybe not all of it, but quite a bit of it. So another thing, a subtle thing about garbage collection cost is that it not only degrades the experience of the game, but because the garbage collectors in general are not deterministic, and the one in Unity certainly isn't, it degrades the predictability of your performance. So it's like this, it's almost this higher order problem. It's like, it's not only could make things worse, it makes it harder to know how it could make things worse. So these spikes could happen basically at any time. So what are the trade-offs here? Again, REPL-driven development. This whole thing was built in a REPL, live-coded. You can tweak it as it's running, which is the biggest win, I think, that Clojure in games development gives you. We have a lot of Clojure's expressive power. Not all of it. We're sort of holding back in the name of performance. We're using mutable types. We're using setbang in places. We're using a lot of interop. But you're programming against a coherent data model where you can selectively move in and out of these two worlds, which is very, very powerful. There is this burden of explicitness. This is something that you need to think about as a programmer. Where do you want to be functional and where do you want to be mutable? And I would also, in fairness, say that the performance of your game will likely degrade as the size of your game increases. So if you're doing a lot of the stuff and more functional programming, you're going to start to see worse and worse performance graphs. But again, if the game that you're working on fits within this profile, there's a lot that you can do. And a game that comes to mind is Temple Run. Has anyone played Temple Run? A bunch of people, yeah. It picks to use examples that are like the top 15 games of the last 20 years. So Temple Run is a game where you're running forward and you're dodging obstacles and picking up these power-ups, and you're being chased by a monster or something. And it's running at interactive rates, right? It's not event-driven. It is, running at 60 frames a second, or at least that's the goal. But a lot of what it's doing on a frame-by-frame basis is the kind of stuff that Unity is good at. It's doing collision detection to see when you touch an object and when you don't touch an object. It's rendering animations. It's rendering effects. I could see an Arcadia-style approach to a game like this, where you're doing the higher level design decisions in Clojure, where figuring out what next track to spawn is happening in a really interesting functional system. But then the actual lower level mechanics are just baked out into some immutable simulation. So this is something that we want to play around with some more as well. And this is the system that you get out of the box in Arcadia. How's everyone feeling? Good? All right, one more thing, and we'll wrap up, and we might have just a few minutes for questions. So I'll go through this fast because none of this is real. This is just future work that I'm excited to get into and explore with. I'm sort of biased because I work on compilers, and when you have a hammer, everything looks like a nail, and when you work on compilers, everything looks like bytecode, I guess. So my gut is that you can use Clojure to use the expressive powers of Clojure to specify a system that you then compile into the fastest thing that we know how to do. And then the trade-off there becomes that you're only doing functional programming on one side of this arrow and none of it on the other side of this arrow. So this excitement comes from a development within Unity. They put out a demo recently called the Mega Cities demo, where even Unity C# programming has performance limits, right? You can't have 100,000 C# implemented game objects in a classically written Unity game. Performance will tank. So it's not, it's not just a problem that Clojure functional programming has. But Unity wanted to be able to make games where you could have tens or hundreds of thousands of objects running around. So it's forced them to reevaluate their architecture. And the Megacities demo is a big example of that. I think I don't know if they get to 100,000, but they definitely have tens of thousands of things zipping around. It's a giant city with a lot of cars sort of flying around, and they avoid each other, and they do interesting things. It's an implementation of an entity component system, which if you've played around with games, that might be meaningful. If not, I'm running low on time, so it's not something that I can sort of deeply define. But this is what ECS code in Unity looks like. This is C#. There's quite a bit of ceremony to it. You're setting up components that make up the different sort of aspects of the entities that make up your game. You're writing systems that grab a bunch of these components and update them. It's all predicated on types. It's all based on structs. But my gut, and this is all that I really have to say, is just that my gut is that you could spec that out as Clojure data and then generate the requisite bytecode to run that. Because the exciting thing about entity component systems is that they do explicitly separate behavior from data in a way that in object-oriented programming, untangling those two things is actually quite hard to do. But in ECS, they're explicitly separate. And I think that actually could be really good for us. So this is something that I want to play around with this year, hopefully. And that would serve as a sort of another angle on what does functional programming and game development mean. Maybe functional programming means you set up the whole thing functionally, and then you bake it down into something that is the fastest thing that we know how to do in this engine. And the trade-offs there, the REPL has been constant through all of these. And you get all of Clojure's expressive powers during development, but then the performance may be as good as C#'s. So that's what maybe is next in this exciting journey. That's all I have to say. This is where the company lives on the internet. That's where I live on the internet, if you're interested. And if we have time for questions, I'd be more than happy to answer them. Thank you. All right. You got a microphone.
Oh, yeah. So I saw there was one of the libraries in Arcadia was kind of like an experiment with Godot engine. I was wondering.
Can you say that again?
Oh, I saw one of the libraries in the Arcadia repo was an experiment of using Arcadia on top of Godot.
Oh yeah.
Yeah. Are you still playing around with that, or is that kind of?
So this is the dream of open source. So I'm not implicated in that at all. That's I think it was Joseph Parker, the person whose screenshot that I showed earlier. And if it's not, I apologize for the mistake. But members of the community put that together, basically by taking our code and making it run somewhere else. So the question is that there's a repository to get Arcadia running in another game engine called Godot, which is interesting in its own way and it's open source. But I think there was some conversations on the community channel about people trying to get back into it. But yeah, I haven't worked on it. So the only thing that I have to say is that I'm very, very excited that people are like taking the initiative to like do that kind of hack.
Awesome, thanks.
Yeah.
Have you looked at anything like CARP specifically as you're like trying to target like the static analysis angle, and if so, like what do you think about it?
Yeah, no, that's a great question. So CARP is a Lisp developed by Eric Svedang, who's a really talented game designer. And my understanding of CARP is that it similarly has no runtime, right? It doesn't have eval, so it's kind of a compile-only Lisp, or it's like a Lisp at compile time only, and then you get this like really tight static binaries. I think I've gotten to build, and I've gone through the tutorials, but there isn't the. I have a bunch of ideas for Lisp game development, so beyond Clojure game development, and there are a lot of things that CARP does that make it hard for us to do and remain Clojure, if that makes sense. There's like kinds of optimizations that you do and kinds of trade-offs that you can make, but you kind of need to stop calling yourself Clojure, because like if you don't have eval at runtime, it's like, well, I guess, you know, you're just a different language at that point. So I think CARP is super interesting from the perspective of Lisp game development. It's a little hard to translate those ideas back into Clojure, if that makes sense.
Maybe it's a kind of not a good question, but I was wondering how the structural sharing either doesn't help enough or to get you out of the allocation problem. That's about it.
That's a great question. So we're currently not leaning on structure sharing, but it's something we're actively looking into. So there's Unity has a quirk that the way that it serializes objects, and serialization happens when you clone an object, for example. It happens in a lot of weird cases that you wouldn't expect it to happen. It will actually deserialize that object into a binary stream, as far as we can tell, hold onto it in its C++ layer. Unity's core is written in C++, and create a new blank object, and then deserialize that into that blank object. So that that makes structure sharing, that's why we don't get it by default, basically. But we are working on ways to sort of be clever and say like, oh, Unity's about to clone me. I know that I have this functional data. Don't serialize this. Just hang on to the reference and pick it up on the other side. So I'm pretty confident that we can pull off some tricks like that, but we're not currently doing it. It's a great question, though.
Thank you.
Thank you.